After studying this lecture, the student should be able to define the reason to slow down of neutrons, explain what nuclear reaction is the best for slowing down, explain main principles of elastic scattering, post-collision energy range, frequency function, average energy loss per one collision, define lethargy of neutrons and its connection to energy. First, I should explain the typical neutron cycle in a nuclear reactor. By default, for simplification reasons, we will consider the thermal reactor. Let's imagine that in the core, in the moment, N1 neutrons were born by fission. Thus, they are fast. What can happen with fast neutrons? The first part of them can fly out from reactor core. The second, the fission reaction can occur on any heavy nuclei, uranium-235 or 38. The next process of neutrons slowing down, and during the process, the neutrons can suffer the resonance absorbing. When the neutron became thermal, they finish their life by absorbing in, for example, non-fuel absorbent, it's bad, or in fuel, but not fissile reaction occurs, it's bad too, and finally, they can produce the fission. We get 200 mega electron volts energy release and 2 or 3 additional neutrons for chain reaction. Then the number of neutrons after whole cycle is N2. N1 and N2 previous and following generation of neutrons, thus K equals the ratio N2 and N1 is multiplication factor of the system, reactor, which takes into consideration all neutron process. For infinite homogeneous medium, the definition of multiplication factor is the same to factor of mu f sigma f and absorption macroscopic cross-section. Please note that to slow down or not, it's our decision. It's our choice of reactor core design. The reason of slowing down lays in dependency of microscopic cross-section of fission. You can see that in fast energy range, sigma f equals about several barns, but in thermal range, sigma f equals hundreds barns. That means in thermal range, the probability to make fission is much likely compared to fast range. In turn, we need less uranium fuel for thermal reactors. They are more simple and cheaper as fast reactor. In this part, we should consider the main laws of neutron slowing down process. And the second, discover the dependency of neutron flux by energy. The last one is called neutron spectrum. How can we slow down the neutrons? Of course, by nuclear reaction of interaction of neutrons with nuclei of medium. We know two types of nuclear reaction, absorption and scattering. All these types have the influence on neutron spectrum. The absorption reaction influence means that after fission, the fast neutrons have certain energy distribution, called fission spectrum. The average neutron energy is about 2 megaelectron volts. The main process of slowing down is scattering. The resonance in elastic scattering can moderate the neutrons. It's important, but it's not main process, because resonance levels for light nuclei are in fast energy range, and for heavy nuclei, the lowest energy level is in the range of kiloelectron volts. It's not enough. The resonance elastic scattering does not moderate neutrons. So the main nuclear reaction to neutron slowdown is potential elastic scattering. Look at the typical microscopic cross-section of elastic scattering. As usual, there are 3 region independency microscopic cross-section of scattering to energy in epithermal energy range. The first is table-length zone. This is potential elastic scattering. The second is resonance zone. This is a resonance elastic scattering. Smooth region too many resonances form the smooth region. So the potential elastic scattering is table length zone independence of elastic scattering. It is limited from the right by the resonance zone, excluded hydrogen and deuterium. For light nuclei, the potential elastic scattering takes place till hundreds of kilo electron volts, in contrast to heavy nuclei, for example, uranium-238, the right border is in the range of electron volts. We can define the slowing down energy range. The following development of laws, formulas, and equations will be true for the region, and it will be our main approximation. The slowing down range is limited from the left by thermal range, about 1 electron volts, and from the right, the first by the border of potential elastic scattering, and the second by condition of isotropy of the potential elastic scattering in center of mass frame. There is an assessment formula to define the energy of beginning of potential elastic anisotropy. E maximum equals 10 megaelectron volts divided to mass of nucleus, designated A, times 3 seconds. So, for example, for hydrogen, there is no anisotropy energy range. Thus, in whole, the right border of slowing down range is about 100 kiloelectron volts. There are two additional assumptions to be continued. The first, neutron impacts to single nucleus. A neutron doesn't feel the nuclear binding in molecule or crystal lattice. The second, before scattering, the nucleus is at rest in lab frames. That means the neutron velocity much more to thermal oscillatory movement of nucleus. This assumption is true for neutron energy above 20 millielectron volts.